In this video, we'll be talking about Pre-Calculus Unit 5 Mathematical Modeling. Some questions that may be answered are, in what ways can the relationship between variables be represented and modeled? What determines the most appropriate representation of the relationship between variables? How can data be represented and analyzed? What insight does the average rate of change of a function give about the behavior of a function? And also, why rewrite a mathematical expression in a different way? All of the questions that were asked from the mathematical modeling learning goals will be answered through the use of 6 great examples. These examples include modeling, solving for variables in context of a problem, using appropriate regressions to determine an equation that models given information, and much more. The examples that are going to be used, which cover this unit, are going to be a polynomial, a linear regression, a rational model, an exponential model, and 2 trigonometric models. One being a way to model a sine or cosine based on a word problem, and one using the law of sines and cosines. Let's begin on our first problem, a polynomial. Squares of width x are removed from a 10 by 25 centimeter piece of cardboard, and resulting edges are folded up to form with no top. The box is 25 by 10 centimeters, and the total volume equation of this box is v of x is 10 minus 2x times 25 minus 2x, all multiplied by x. This is because the volume of a cardboard box with no top is length times width times height. So you plug this equation into your graphing calculator to find the maximum volume that can be inscribed into this box. The x value is 2.201, which is what equals x. Next, we are asked to determine all values of x so that the volume of the resulting box is at most 175 centimeters cubed. To do this, enter y equals 175 into your graphing calculator and find where the points intersect. You find where the points intersect by pressing second trace intersect, and you will get 0.29, 175 and 3.044, 175. These are all values of x. These are the minimum and maximum values of x that is resulting so that the box is 175 meters cubed. To find the dimensions of each part of the box, the length, width, and height, you plug in 2.01 for x, which is the height. Therefore, the width is 10 minus 2 times 2.01, which is 5.98 centimeters, and the length is 25 minus 2.201, which is 20.598 centimeters, and together the total volume is 253.792, which is what the y value was in the absolute volume maximum. Our next problem is a linear regression problem. Chrissy bought a computer for her home office and it depreciated over 5 years using the straight line method. If its initial value was $2,350, what is the value 3 years later? To begin, after looking at the graph of this model on your calculator, you would find the slope of this linear model using y2 minus y1 over x2 minus x1. This would be 0 minus 2,350 over 5 minus 0. This equals negative 470, meaning that it's negative $470 per year that it depreciates. Then you plug into your equation using the b value, 2,350, because this year is 0. So the equation would be p equals 2,350 minus 470t. When t equals 3 after 3 years, Your final answer will be $5,940 after 3 years of depreciation. The next question is a rational regression. The total amount of sales in billions of dollars by fast food business for several years is modeled through the function f of x equals 120 minus 500 over x plus 8. This can be used as a scatter plot and plugged into a graphing calculator. If you let x equal 0 represent the year 1990, and the question is asking to estimate the amount of sales by the fast food business in 2005, what you would do is plug in 15 for x because 2005 minus 1990 is 15. After plugging in 15 for x, you will get $78.7 billion in fast food business sales. You can also find this by plugging it into your graphing calculator and intersecting where the year 2005 or year 15 is, and you can find the y value. Our next question to cover is an exponential function. The population of Smallville in the year 1890 was 6,250. Assume that the population has increased at a rate of 2.75% per year. The question asks what the population is in 1915 and 1940, and also when will the population reach 50,000? To begin, you have to identify your variables and plug them into your equation. You can use the equation P of t equals P initial times e to the rate times time. In this problem, our rate is 2.75%, which translates to 0.275. Our P initial, which is our population, and the initial time it was given is 6,250 people. There you can plug in the values that are given into our original equation. So P of t equals 6,250 times e to the 0.0275t. Next, we are asked how big the population of Smallville will be in 1915 and in 1940. So in 1915, that is 25 years after 1890. So you plug in 25 for t, which is P of 25 is equal to 6,250 e to the 0.275 times 25. This gives you 12,429 people. Next, we're asked to do the same thing but for 1940. This is 50 years after 1890, so plug in 50 for t. So our equation is 6,250 times e to the 0.0275 times 50. Our answer nearly doubles because it's 25 years after 1915. So our answer is 24,719. In part B of this question, and a lot of exponential modeling questions are asked, this question is asked, when will the population reach 50,000 people? There are many ways to do this. One way is that you can graph y equals 50,000 along with your exponential model, P of t equals 6,250 e to the 0.0275t, or you can do it manually. So you set 50,000 equal to 6,250 e to the 0.0275t and solve for t. To do that, you divide by 6,250 on both sides, and then you take the natural log of both sides. So this ends up being the natural log of 8 equal to 0.0275t, and you divide by 0.0275 on both sides. This equals 75.6 years. So you add 75.6 to the initial year, which is 1890, and this is about 1965 towards the beginning of 1967. Now on to trigonometry. The bottom of a Ferris wheel is 4 feet off the ground. The radius is 30 feet. You begin moving continuously at the top of the wheel, and it takes you 8 minutes to complete one rotation. First, we are asked to graph this model and write an equation that models the height from the ground as a function of time. To graph this model, you would start at 0,64 and progress in a cosine function all the way to 8,64 after the first rotation is over, which is our period. To find this equation, you would do the amplitude times our function x with our period inside plus the midpoint. So this would be 30, which is the amplitude between the midline and both 4 and 64, cosine, and then the period next to x, the period is 2 pi over b, which is 2 pi over 8, and that translates to pi over 4, plus 34, which is our midpoint. And x is equal to time in minutes. So we are asked at what time during the rotation are you 30 feet off the ground? This can be found through graphing y equals 30 onto the function of 30 cosine pi over 4x plus 34. You get 0.919 comma 30 and 3.793 comma 30. And these are the time in minutes. So 0.919 minutes and 3.79 minutes are in which you are 30 feet above the ground in between those values. In our last part of this problem, we are asked to model the same situation but use sine. This is very simple in that the only difference is that sine is shifted over to the left 2, which is really 1/4 of our period. If you draw that, it shows how sine is just moved over slightly, and our new equation is 30 sine pi over 4x plus 2 plus 23. Our last problem is using the law of sines and cosines. Two remote islands, B and C, are 300 miles apart from each other. The boat at point A knows that it's 550 miles from island B and 350 miles from island C. The boat is currently heading towards island B, but it wants to know the angle it should turn to head towards island C. So, using this information, we should find what the angle that the boat should turn at to most effectively arrive at island C. Because we are given no angles A, B, or C, and we are told to find them, we need to start by using the law of cosines. The law of cosines is a squared equals b squared plus c squared minus 2bc cosine A. So, this really is a equals cosine inverse of a squared minus b squared minus c squared all over negative 2bc. So you plug in your values and you get a equals cosine inverse of 300 squared minus 350 squared minus 550 squared over negative 2 times 350 times 550. After all the calculations in the parentheses, you get 0.870. So you take the cosine inverse and you get 29.53 degrees, which is the angle A at which the boat should turn to most efficiently get to a remote island C. In part B, we are asked, at what angle would the boat turn upon arriving to island C to get to island B? Well, now that we have angle A, we can use the law of sines to get our answer most efficiently. So you take sine C over 550 and set it equal to sine A over 300, which sine A is 29.53 degrees. You cross multiply, and then you take the sine inverse of 550 sine 29.53 over 300, and you get the angle 64.64 degrees. If you want to find the third angle, which is angle B, you can add 64.64 plus 29.53 and subtract those from 180, and you get the angle of 85.83 degrees. In the last 60 minutes here, we've used polynomials, rationals, exponentials, linear regressions, and trigonometry to model real-life situations and interpret them in different contexts. We've learned that there are many ways to complete a problem, whether it's by hand, by graph, or by a variety of methods such as cosine and sine. All this analysis will give us a better understanding of math and pre-calculus and how we apply it to our everyday lives.